All right. Welcome to lecture 3 on the mathematics. Oops. The ma- the mathematics of data models. This is Northeastern University's course, and I'm Professor Wu in the College of Computer Science. So here's a problem you may have seen on the SAT. All right. A concert charges $20 for adult tickets, $10 for student tickets. If the concert sold 100 tickets and made $2,000, how many of each type of tickets were sold? Okay, you should be able to solve this. If you want, pause the video and see if you're able to solve this. Okay, here is a problem, right? Here is a problem that you may have seen. And the way you solve it is that the problem essentially gives us two pieces of information. First, we're going to let A represent the number of adult tickets sold. And we're going to let S be the number of student tickets sold. Then we know that adult ticket plus student ticket is 100, or A plus S is equal to 100. Now, if you remember, it said it right here. The concert sold 100 tickets. So that's one piece of information that we have. Next, we know that it made $2,000. So the number of adult tickets times 20, the price, and the number of student tickets times 10, the price, total is $2,000. So now that we have two equations and two unknowns, we can essentially solve them. Now, with just one equation, it's a linear function. But if you have multiple of them, it's called a linear system of equations. The standard way we learn to solve this is through substitution, right? So let's look at the first equation. We can essentially rewrite it in terms of A. Once we know A, we can plug this back in, right? We plug A in here, which this is A here. Now there's only S. This allows us to solve for S, which S is just equal to 0. So it is saying that there were 0 student tickets. Now, this approach of substituting is really useful when there are only a few variables. But what if you have a bigger problem, something like this? You will be substituting a lot of things, and not exactly the best way to solve this problem. So, our goal today is learn how to solve bigger problems like this. Okay? And this process is called Gaussian elimination. So, Gaussian elimination, it's all about the truth. So we're going to learn the three noble truths. Well, the three conclusions we're going to learn. Well, let's say that we have a vector x and two functions defined as this. Okay, so we have two functions. We're going to say that each one of these functions, when given to you, you're going to assume that they're true statements. 2x1 plus x2 is equal to 1. That is going to be a true statement. And you're going to assume that this is also a true statement. And you want essentially to find x1 and x2 that makes both statements true. Okay? Now, in this case, we're going to open everything up so we know the x1 and x2 that makes both statements true is 1 and -1. So we're just going to know that. Like normally you're trying to find it, but we're going to open everything up so we can study what's going on. Okay? So we can see that if we plug 1 and -1, right, you plug them into these equations, they end up to be true statements. 1 equals to 1, true. 1 equals to 1, also true. The interesting fact about true statement is that they can be manipulated and remain true. For example, we can multiply both sides of the equation by a number. So this is a true statement. Now, if we multiply both sides by 2, here and here, well, this is still a true statement, right? Now, let's verify equation 4. Let's verify it. So let's plug this in. And notice, if you plug 1 and -1, you got a statement where it's 2 equals to 2. It's not the same statement anymore, but regardless, it's still a true statement. So even though we have two statements that look different, right? They're different, but they're both true. Okay? We're going to symbolically represent what we just did in equation 1 as 2e. What happened is we took equation 1 and we multiplied by 2. And when we did that, it gave us yet a new statement, and that is still true. Now, there are a couple of factors to note. Okay? There are a couple of factors to know that a true statement can be manipulated when there's equal sign, right? So if you have 3 times 3, so 15 is equal to 15. If there are no equal signs, like if you're 5 feet tall and you can't just multiply 5 by some constant value and tell people you're 6 feet tall. That doesn't work. You need some kind of equal sign like this. Okay? These mathematical true statements are only true given a particular value. So if you plug 1 and 0, they're no longer true. So there's some x value that can make both of them true. So under the correct condition, the truth can be manipulated and somehow remain true. This allows us to conclude the first observation. The first observation says that the result of multiplication and division of true statements on both sides is still true. Essentially what we just did here. Right? Now, we learned this in algebra. Right? Very often we solve algebraic equations by doing the same thing on both sides of the equation. So this is not exactly something shocking. Okay? In fact, all 3 observations I'm going to tell you today are not something shocking. Yet, when you put them together, you are able to solve like really complex problems. The second conclusion that we're going to look is that if you have 2 equations, the same 2 equations we were talking about, this is the original 2 equations. If you not rotate, but swap, if you swap the 2 locations, these 2 statements are still true. Just because you moved it here and over here, you swap the 2 locations, it doesn't make them less true. Okay? An apple, if you move the apple to a desk, the apple is still an apple. Right? It doesn't make it any less apple, the location. There, we see that equation 1 and equation 2 has become equation 2. So, and vice versa. We're going to mathematically represent what we just did as E1 and E2. Now, in real life, the order of presentation obviously make a big difference, but here we're just talking about mathematical equations. So, for these mathematical equivalences, the order doesn't matter. You can swap them and they'll still remain true. The third conclusion that we'll come to is that if you have 2 statements, the same two true statements that we talked about, the combination of 2 true statements, the result is still true. So let's try it. We're going to add them together. So 2x1 plus 0x1, that's 2x1. And then we're going to add these together, which is 2x2. So now that leads us to a new statement. 2x1 is equal to 2. If we plug x1 in here, is it still a true statement? Yes, 2 is equal to true. 2. So, still a true statement. Now, we're going to symbolically represent what we just did. Combination of equation 1 and equation 2 as this. Okay? And as I showed you previously, if we plug 1 in here, 2 is equal to 2. So, that leads us to the third conclusion. The summation or subtraction of 2 true statements yields another true statement. Now, if we combine all 3 conclusions, okay? So, let's combine all 3 conclusions. Remember, we combine equation 1 and equation 2, right? And we're going to let equation 1 and equation 2 equal the new equation 1. So, the new equation 1 is going to be right here. And we're going to keep equation 2 the same. So equation 2 right here, still the same. Okay. Now let's perform another operation. We're going to multiply equation 1 by half. Okay. If we multiply equation 1 by 1/2 and let that be equation 1. So we're going to do multiply by equation 1, and that's going to become the new equation 1. Then the new equation 1 will be just half of this. So x1, 0, and 1. Notice how it's half. We've essentially divided by 2. Still a true statement. Remember, we multiply by half. You could have multiplied both sides by anything, and it still remain true. Okay, so half of equation 1. The next thing I'm going to do is I'm going to multiply equation 2 by negative 1. So equation 2, I'm going to multiply by negative 1, and that's going to become the new equation 2. So what happens? If you multiply negative 1 here, negative 1 here, you got a positive and a negative. So at this point, what has just happened? Well, this is 0 and this is 0, which means we yield the result, a new true statement. So this statement must be true. And that statement is x1 is equal to 1, x2 is equal to negative 1. So what just happened? We essentially converted the original equation, 2 equations, and by manipulating them over and over again, we end up in a form where we have x1, x2, and 0 everywhere else. And when you have manipulated the original equation into this form, it implies that now you essentially know what x1 and x2 is. So we've solved the optimal x1 and x2 by transforming it into this form. Again, this form is when you only have x1, x2, and their constant is 1, multiplied by 1, multiplied by 1. Whereas everything else are zeros. And when that happens, you have the problem solved. Now, in this example, like I told you, we already know what x1, x2 is, and look how it match. However, most of the time, we don't know. We don't know what x1, x2 is, and we're trying to find x1 and x2. Okay? So the goal, right, is to manipulate. So here's 4 equations and 4 unknowns. So you keep manipulating them so that you end up with the diagonal terms, x1, x2, x3, x4, equals to whatever value here, because all the off-diagonal terms are 0. And once you reach this point, you know exactly what x1, x2, x3, x4 is. You know what they are right here, these values. So that is the name of the game. How do you manipulate truth until you reach something like this? Okay. And this is when you can, like, it essentially tells you the solution. Okay. And this process of keep manipulating the truth is called Gaussian process. Okay. Now let's look at a simple example. Okay. Given the following system of equations, we can first multiply by e2. We're going to first multiply e2 by 2. Okay, so here we go. We're going to multiply e2, second equation, by 2. Now I multiply them by 2. This is times 2, times 2, times 2. Once we multiply by 2, we can add them together. We're going to add e1 and e2 together, and I'm going to let whatever that result become the new e1. Okay, so let's add them together. So this is cancel out. That equals to 4, and that equals to 4. So we have 4 cancel out and 4. That's how we got it. So I manipulate this again. What am I going to do next? All right, I'm going to copy this here. Now let's look again. What I want to do now is I want to divide E1 by 4. Now, why did I want to divide this by 4 and let that be the new E1? Well, because we want this to be gone. We want this to be 1, right? And we want this to be 0. So notice how we achieve a 0 here, okay? So if I divide E1 by 4, so divide by 4, so we got 1 and 1 here. Okay, now let's copy this again. What do we do next? Well, I'm going to multiply minus 2 times E1 and then plus E2. And that's going to give me the new E2. So let's see. Minus 2 E1, x1, and then 0 equals to minus 2. Right? If I multiply minus 2 here, and I'm going to add to E2. 2x1, 2x2 is equal to 2. So that's 0, 2x2, 0. So this is going to be the new E2 right here. So now we're very close. We want that to be 1 as well, so we can just divide both sides by 1, right? So I'm going to take E2 here and divide by 2, which give us the final form. At this point, we know what E2, 1 and E2 is. E1 is 0. Sorry, E1 is 1. E2 is 0. So we have x1 is equal to 1 and x2 is equal to 0. So the problem is now solved. We can double check our solution by plugging it back in. So let's plug in 1 and 0, 1 and 0, 1 and 0, and see if the statement is still true. So 0 times 2, 0. So 2 is equal to 2. That's true. Next, 1 is equal to 1. So both true. Both statements satisfied by this right here. So not bad. Now, let's look at some notation simplification. Given the following system, right? Here's the system. And then you saw we did all these things. But notice we have to write x1 and x2 over and over and over again. All right? You're just copying over again. Now, when we do Gaussian elimination, so far we're copying them. But we don't really have to. So instead of writing the two equations, we can write them in a matrix format. And the matrix format is 2, 1, 0, minus 1 times x1, x2. We learn how to do matrix product, right? So we know how to do this multiplication. If we do the dot product here and here, notice that's just equal to this equation. Right? Take a second, make sure you're convinced. Now, if we take the dot product here, notice it's just this equation, right? So now, since we know this is always going to be here, we can just ignore x1 and x2, and we just write it in this format. And this format is called augmented matrix. Therefore, instead of constantly copying, you can just multiply it by 2, only the number, and don't really have to worry about it. Okay? Now let's solve a system of 4 equations. So this one's 4 equations. So over here, right, first thing we do is we create the augmented matrix. I just showed you this. And your final goal, we don't know this is yet, but we'll fill this in, is that on the left side, you want all ones. Remember that was x1, x2, x3. So it's 1 times x1, 1 times x2, 1 times x3, so on and so forth. So this is your final goal, okay? Here are the first steps we take. So notice E4 already has 1 at the start. So notice that E4 already has a 1. So why don't we just put that at the top, because then that simplifies things. So the first thing we're going to do is we're going to swap E1 and E4. So E1 and E4, we're going to swap them. So after the swap, notice the top one, that's E4. Now it's E1. And E1 is now E4. Okay, now that we've done this, the next step we want to do is I'm going to, like, once you've done this, you essentially want to get rid of all of these. right? You want to zero them out, right? And once you have a 1 here, it makes zeroing them out actually really easy. You just multiply this by -3 and then add to this one. And then you're going to make sure this is 0. Again, you can take the first row, multiply by -2, and then add this one. Notice -2 and 2, it will cancel each other out. So that's exactly what I'm going to do. I'm going to take the first row, multiply by -2 for this, and multiply -3 for this one. And I'm going to add them together. Once I take 2e, I'm going to add to 4. So I'm going to take -2 here, and I'm going to add it to this one. And that's going to replace, that's going to be the new e4. And then I'll do the same thing, multiply -3 here, and add to this, right? -3, add to equation 2. And that's going to become the new e2. After you do that, you basically got zeros here. Okay? So that's, now we've created 0. Here, you want to have a 1 again. Luckily, it's already 1. And why do we want a 1? Remember, once you have a 1, it's very easy to get rid of everything else. You can turn that into a 0. You can turn that into a 0. So we can just take this one and essentially multiply by -2 and -4, and then combine with these two. Once you do that combination, you will be able to zero these out again. So every single time you zero them out, you end up with a smaller problem. Notice it's red here. You don't have to worry about these anymore. You already zeroed them out. And once you solve all the zeros here, it now once again becomes an even smaller problem. And then even a smaller problem. Okay? So each time you're like decreasing the dimension. So remember, let's say I multiplied this by -2 and -4, and I zeroed these two rows out. Okay? So -2, -4, like I told you. Now, all these are zeroed out. And you don't have to worry about this column anymore because they're all 0, right? Once you've achieved that, well, now you have even a smaller problem, right? Every single time, it's a smaller problem as you get smaller and smaller and smaller. Next, well, we want a 1 here. We don't want a 0. So we can swap the two. I'm going to swap the two so that the 2 is here. Now, remember, I want this to be a 1, right? So I'm going to divide it by -2. So this is a 1 again. And this one, I'm just going to divide by 6. So this is also a 1. Okay? And now we've achieved the minimum form to obtain the solution. This is called the row echelon form. The row echelon form is just when the bottom part are all zeros. Remember, we previously, ideal case is we have the top triangle and the bottom triangle all zeros. But if you reach this form, it essentially allows you to solve the solution pretty easily. So how is that the case? Okay, so you have reached the reduced echelon form if the bottom triangles are all 0 and the diagonals are all 1s. Okay, notice that the upper triangle doesn't have to be all zeros. But this is enough for you to get x1, x2, x3, x4. How is that? Well, let's say we start with this one. Well, we know what x4 is, right? It's just by looking at this equation because everything else is 0. So we can solve for x4. Now we can plug this x4 here. So we know everything here and this one. They're just constants. If we know everything here, we can solve for x3. Okay, now we know x4 and x3. So we know x4 and x3. So these are constants. These are all constants. So all we have is x2, right? So we can solve for x2. Now we know x2, x3, x4. So the only term is x1. So we can solve for x1 again. Because in the end, we're going to know what each one of these is as you iteratively go backwards. Okay. Now, if you were to keep going so that the upper triangle are all zeros as well, then you will reach the reduced row echelon form, right? Once you have echelon, row echelon form, it's easy to continue, and then we can find the final version we want. The ultimate version is the reduced row echelon form. Okay. Now, remember the way we went about it is we got a one here, and then we can zero everything out here, and then we got a one here, and then we can zero everything out here, and then we got a one here. We can zero everything out here, and then it's pretty easy to get a one here. Okay. So once you have reached the row echelon form, you can now go backwards. You have a one here, right? So you can easily zero these out, right? Now you have a one here. So now that these are zero, you can easily zero this out. You have a one here. So you basically go this way. You basically go this way to get all the zeros. And then this one becomes a one. And you can go backwards like this. And if you follow this trajectory, you would essentially reach the final form. And in this final form, the solution is simply whatever is right here, right? X1, X2, X3, X4. The reduced row echelon form is, let me see. Okay. So the reduced echelon form is the preferred form. This is the preferred format. And this is the format we're going to ask for during the exam. Okay. So this is, and there's a reason. In the next lecture, it'll become more clear why the reduced echelon form is the preferred form. But you got to remember, if you're just trying to solve for x1, x2, x3, x4, and if there's a good solution, then yeah, you can use the row echelon form, REF. But most of the time, like you want to go with reduced row echelon form, and we'll show you why later. So you want to pause the video, see if you can solve this yourself, and we're gonna go on. After you pause the video and solve it, we'll show you the solution. Okay, so make sure you can follow this along. Okay, go through this at home. This this is the solution. Okay. So yeah, so this is a solution where we reach the row echelon form, and then we continue and we solve for the reduced row echelon form. So this problem here, we showed you how to do it all the way to the reduced row echelon form. After this, try again. It takes a lot of practice to get it. Okay, here's the solution. Okay, so pause the video. Once you've solved it, you can check out the solution, see if you got it right. Right? If you don't, try again. It takes a lot of practice. When I was learning this, I was super confused. And the way you solve in Python, well, here's A, here's Y. Remember how we formed the matrix A, and it was A here. A times X is equal to Y. So right here, see, this is the matrix form, and the Y is right here. That's right here, 1, 3, 2, 1. Okay, once you declare this equation, you can essentially just call linear algebra solve, and it'll give you the solution. See, this is the solution. Life is much, much easier. When you're working, you want to do this. Right now, I want to make sure you know the mechanisms, like what's going on when you're calling this function, which is the Gaussian process that we just learned. Okay, you can get reduced row echelon form with this package called SymPy, symbolic Python, which you can download, or you can just run the pip command for it. And this was that same matrix that we had, right? This matrix here. So if you follow the code, you create the matrix, and then once you have the matrix, this is the augmented matrix. Sorry. So this is the augmented matrix. Once you have the augmented matrix, you can go called RREF. And then once you have REF, this right here, if you print out the first element, it will give you the reduced row echelon form. Much, much easier. So essentially, when you are solving homework problems, you can just check your answer yourself and see if you got the same thing. Okay. Now remember, we solved it previously. It was 102. Right. Notice 102. So you can find the solution this way. Okay. Final exercise, and that's it. Take a look at this. Pause the video. Make sure you can solve this, and once you solve it by hand, you find the REF, you find the RREF, which give you the solution. Then use Python to get the answer. Okay, whatever you get from Python should match whatever you solve by hand. If it doesn't, there's a problem. And you got the solution X, right? You can always plug X back in and multiply by the original matrix, and that should give you Y. So download SymPy and try it, and then make sure you submit your result. Okay? So yeah, good luck. I'll see you in the next lecture.